Yeah, hi everybody. So our next speaker is Basil Saeed from Stanford. Please join me in welcoming Basil.
Thank you. Can you hear me? Is this on? Yeah. Okay. So I'm going to be talking about this recent work with the same name that's joint with Kiana, Asgari, and Andrea Montanari, and I think both of them are in the audience. And before I tell you what this is about, I want to first introduce the setting in which we're in, the empirical risk minimization setting, where I'm given features x1 up to xn that are in RD. Put assumptions more on them later. But for now, I'm assuming I have labels yi that are some function that look like this. Theta 0 transpose xi and wi, and I'll take my labels to be in RQ for some q. And theta 0 is a matrix that's in RD by k. And wi are just IID noise from some distribution, PW. And I'm going to fit these features using empirical risk minimization. So it's the standard stuff where I minimize theta. And for simplicity, I'll take the dimensions of this same as the ground truth that I'm assuming. Loss function and my ridge regularizer. And here I'll assume that lambda is bigger than or equal to 0, and I'll allow it to be 0. Okay, so what I'm interested in, so this is going to be a talk about tools. So I'm going to be interested in tools for precise asymptotics. In high dimensions. Maybe I'll stop for a second and ask if everyone can read my handwriting or if I should slow down. Okay, yeah. What this means.
In the ERM, the model is linear, right? There's no psi in the model.
Sorry?
In the ERM, the model is linear.
I mean, this depends on what your label distribution is, right?
Right, the label, so it's a misspecified linear regression.
Sure, I mean, I consider it a general linear model, for instance. Example is a generalized linear model.
Just to make sure, when you do the ERM, the model is linear. The parameter is
linear. In this case, so yeah. I mean, okay. I mean, not necessarily, no. I mean, you can think of this, I'm using this in a generalized sense. Like, for instance, I can take this to be L of f of theta transpose xi. And some yi like this, right?
Oh, okay.
And I'm just lumping this. I'm going to make assumptions about this quantity, right? Okay. And whatever assumptions that implies about something like this, you know. But I haven't made my assumptions yet. I'll tell you what these assumptions are. Okay. Sorry.
That function rho.
Rho psi or L, yeah. L is fixed, yeah.
Oh,
L is fixed, yeah. Sorry. This is my last L, yeah.
So for instance, two-layer neural network with k neurons.
Okay, but I'll make assumptions exactly about what this is, and but for now I need to tell you what this is, what this means, in case you're not familiar. So the high dimensions means I'm going to take my dimension d to be some function in n, and I'm going to be looking at the following limit, where n over d converges to alpha. That's constant as n goes to infinity. So I'm looking at this limit across spaces. And I'm interested in quantities of the form, say, g of theta hat n, computing exact asymptotics of this quantity. This converges to some g star, and this g star will be some function of alpha. Other quantities like pw, maybe the norm of theta 0 if this is fixed, etc. Okay. For instance, this can be estimation error, prediction error, more generally, statistics of your Hessian at the minimizers, and so on. Okay. So just because I think maybe not everyone's familiar with these things or these precise asymptotics, so I'm going to take maybe 10 minutes to talk about just background, a little bit of background on precise asymptotics. So maybe I'll write the outline here. First, I'm going to just do a little bit of a background. Then I'm going to tell you what our approach is, our results. And if at the end there's any time, maybe I'll go a little bit over the proof. Okay, good. Okay. So let me start with examples. Examples of some of the phenomena that we can capture via precise asymptotics. Okay, the first one is the one we all hate and love, double descent. And here I'm thinking about theta hat n being the minimum norm interpolator of some model. And I'll be interested in our theta, let's see, our test theta, defined as expectation for a fixed theta, defined as y plus minus x plus transpose theta squared. Where here the expectations over y and x. And I'll compute our test of theta hat n, the limits of this in this regime, the regime that I outline here. And this converges to some RS star of alpha. For instance, one paper where this was studied is this paper, HMRT 20, and they showed that you can see in this regime, in this limit, that if you plot 1 over alpha against this guy, you can see the double descent phenomenon. And the qualitative behavior of this curve, whether it goes up, or, whether it goes above or below the initial point, depends on other things. And some of the other things it depends on, for instance, are the distribution PW or norm theta 0. Okay. Okay, some other phenomena. Phase transitions. For instance, for the existence of MLE or separability of the data. Here I'm thinking of something like yi plus or minus 1, and the probability that yi is equal to plus 1 given xi is something like g of xi transpose theta 0. And say I do theta hat n to be the MLE, the logistic MLE. Now I can plot in the space of 1 over alpha norm theta 0. So if I look at the limit of this problem in this regime, I can show that I obtain the following curve that splits this region into two. One region under which, with high probability, the MLE exists. And here, with high probability, the MLE does not exist. Oh, sorry. MLE does not exist here. So here is increasing N over D. So here the MLE exists.
What does that mean? Exist or doesn't exist?
The MLE. So in here, so if you as you increase the parameter space, the data becomes more separable, and so there's a direction in which you separate the data. So the MLE diverges.
Succeeds or not? Doesn't succeed.
So with logistic regression, you want your data to be non-separable for you to converge to something. Otherwise, you want to add some kind of regularizer or do max margin separator.
And also, what is the role of psi here? There's something called dependency, or your results, the results that you showed.
This guy?
Yeah.
So I guess this is just going to be my the general model that I have for my data yi. Okay.
All of these results do also depend on us, right?
All of them, of course, dependency. Yeah, of course. I mean, this, yeah, so C is implicit here, whatever distribution you get from this guy. Insane. I mean, I haven't really specified what the data generation process is here, but I just want to give a taste of these kinds of results for now. Okay, I'll say some example. I mean, where this was done, for instance, in Candister 18 for the logistic case, and this was done via technology called approximate message passing, or AMP. And more generally, this was done in MRSY, where they showed this separability transition threshold for more general functions than the logistic, and it was done via some technology called Gordon. And I'll say a little bit about what these things are. Okay, but now I want to just to give an intuition about these precise asymptotics tools. I want to say give you intuition about why they succeed at characterizing the limits so accurately. Okay, and I guess the one line punchline is that their success is because they're really good at localizing the minimizers or the minima of R hat n. And to say what that means, for me to explain what that means, let me restrict to the strongly convex case. Convex, where theta hat n is unique. Okay. So that localizing the minima is about localizing the minimizers. I'm going to say that. So these techniques are really good at finding some set S, such that the probability that there exists a theta in S complement satisfying R hat and theta equals 0 goes to 0. And this set S is very small in some sense. And I'll show you why that is. For instance, the AMP technology. Okay, if you're familiar with AMP technology, see this as a review. If you're not familiar with it, maybe this will be the introduction. But this is a very abstract and perhaps not the most accurate introduction.
Probability there exists theta in S complement such that
probability that there is such that the gradient of R hat n of theta. So I'm localizing. So yeah, so I want to choose my S to contain the set of theta that I'm interested in, the minimizer, right? And I'm claiming that AMP and Gordon, technologies like AMP and Gordon, let me choose this S to be small in some sense. And I'll show you what that is. I'll give you an example of what the size of S is. Okay. So the AMPL analysis on an abstract level proceeds something like this. You create some kind of algorithm. Iterative algorithm. Think of it as some descent algorithm that's modified in some way so that it's easier for analysis. And for a fixed t, it satisfies this as t goes to infinity. So it converges to a critical point that satisfies gradient of. So it converges to the point R hat n that satisfies this guy.
Capital X is that like.
This is the data. Yeah. Okay. Maybe, yeah. This is the data. I guess this is the data that I haven't introduced yet, but I haven't introduced the notation yet. But x1 to n. Let's say this is my. So what I'm saying is that I'm using the setup that I have here to create some descent algorithm. This is just the standard stuff. Okay. Now for this algorithm, I show. Okay, so I know for a fixed n that this converges to the minimizer. For this, I show that I can take the following limits. Limit as n goes to infinity first, then limit as t goes to infinity is equal to 0. So that I can commute these limits instead, and I still converge. And then I analyze this fixed point star. Analyze the asymptotics of star at fixed t. And the limit as n goes to infinity. Okay, now we need to agree on a way to analyze this in the limit as n goes to infinity, because once again, this limit is across spaces. Okay, so one reasonable way to do that is to do it in terms of empirical distributions. I'm going to define the empirical distributions of theta hat t to be 1 over d square root sum of j equals 1 to d delta at root d theta j t. And this is just normalization because I want to take my theta to be order 1. So if you're uncomfortable with this, ignore it. And now if I take the asymptotics of this, I obtain some fixed point equation in terms of measures.
Dimensional. T is not the same as this. Oh,
Sorry.
okay. So you're taking the. There's 3 things. There is dimension, there is time t, and there is
Right.
the sample size there.
The dimension is a function of n. So whenever I take n to infinity, I'm taking d to infinity, right?
Okay, effectively you're increasing.
And I'm just saying that this is, I'm trying to make sense of the limit of this quantity in some way. Because this is a quantity of a d equals some d-dimensional vector equals some d-dimensional quantity. The way I'm going to make sense of it is by doing it on the level of empirical measures. Because this is something that's fixed as I take. The space is fixed at least. Okay, so I'm going to write down what the empirical distribution of some point theta t is. And as I take this to infinity, this becomes some kind of fixed point equation, some kind of iterative equation in these empirical measures for each t, exactly, for each t, right?
Sorry, just a question. So is the idea here, like the intuition is that in the limit they become almost like IID or something like that? The thetas, like
not necessarily. I'm not saying anything about the coordinates being IID or not. Nonetheless, I can still take the empirical distribution of the coordinates, right?
Okay. There's usually like a mean field limit where you have these particles or something.
So, okay, I'm not going to talk about the dynamics, I guess, in this. I'm just trying to give, I guess, intuition about what these kinds of things do. Okay, no, the point is that this is some kind of fixed point equation some kind of iterative equation in t, right? And I'm going to take the limit now as t goes to infinity to obtain some fixed point equation of this form. This has the interpretation that in some sense this is the asymptotic version of this fixed point equation, which it would have converged to if I reversed the limits. If I first went n to infinity, then t to infinity, then n to infinity. So this specifies conditions on the empirical distribution of theta, such that when it's satisfied, I would expect that this is satisfied. So the set S that I'm going to use here will be something like the set of theta, such that the empirical distribution of theta for some distance d is bigger than epsilon, where mu star is the solution of this guy. Yeah.
Just a quick question. So is the order of the limits very important in this case?
Yeah.
All right.
F depends on the data. F2.
It depends on the distribution of, F depends on the data that I have. F tilde depends on the distribution of the data and other parameters, because F tilde is the limiting, it's the limiting functional, right?
Okay, I guess because you take n equal to n.
Yes. Good. Okay, maybe I'll also, since I went through the hassle of doing all this empirical distribution stuff, I'll also give a one word about Gordon and show that it's the same idea. With Gordon, the workflow is a little bit different in that you compare the empirical risk that you're originally interested in to an empirical risk of a simplified to the minimization of a simplified empirical risk that looks something like this, where r hat simp is just some simplified version of empirical risk. And this holds in the limit as n goes to infinity. Now, under convexity, I can show that in some sense, theta hat n is close to this is the minimizer of this guy. The exact sense is that under test functions, this is 1. So this tells me to obtain conditions on the optimality of this, I can analyze this one instead. And it turns out that this is simple enough such that if I just look at the gradient of this simplified problem and set it to 0, I can directly analyze its asymptotics to conclude a condition like this, f tilde mu star equals mu star. And I'll call this f tilde 0. Sorry, people there can't see, but it's not much. Okay, maybe I can move this guy. Okay, but is this clear? Yeah, okay. Okay, maybe just to hammer the point one last time, or for one last, minute, it would be useful to compare this to maybe a thing that's more familiar to people, which is uniform convergence. And in uniform convergence, the quantity that you want to look at is something like this. The population. And you bound something like the supremum or theta in some function class, and let's say the function class is just an L2 ball. If I look at the VC dimension here, this is going to be something of the order. This bound you get is something of the root d over n, which in this regime is order 1, because I'm assuming that d over n goes to alpha, or n over d goes to alpha. So the picture in uniform convergence looks something like this. If this is your theta 0, you obtain some sample. So this is, let's say this is your this is your population risk, and say that I've set up my problem so that theta 0 is the minimizer of my population risk. And if I sample some r hat n, it looks something like this. And uniform convergence tells me that the maximum deviation is going to be on the order of 1 asymptotically. Okay. So now if I try to do something similar here to find some set S, such that the probability that there exists a theta in S complement satisfying some condition on this guy, say for instance, let's say this guy, compared to the population minimizer, I need to take this set theta to at least include everything here. Sorry, this set S, I need to take it to include everything here, which is quite a large set. So if I want this to go to 0, I need S to be large. As a result, there's no hope in me to localize, to find some S that localizes minimizers accurately.
How do you solve it?
Huh?
How do you solve it?
No, I think this is just this is a part of, this is just the fact that this guy, this guy doesn't concentrate. This quantity doesn't concentrate as a function, but r hat n, theta hat n at the minimizer concentrates. So the conditions that I'm going to use will be about this guy. So this one in particular.
Intuitively speaking, like r hat theta should have less coupling using the random variables. Feels like r hat theta hat has more coupling.
More covering?
More coupling.
Coupling.
Like random variables are more coupled with each other. Why?
This random variable and this random variable?
That one. Why that concentrates well? The first one doesn't.
I think because they're coupled is what makes them concentrate well, right?
I guess really what it means is that the soup over theta. I mean, the soup over theta, but the soup over theta can be large. Like there is theta such that is very different from the expectation. It means what he brought above. Right? Oh, I see. It's a soup, not just the theta zero.
No, not at theta 0. No. I'm thinking of it as a function, I guess. Yeah. Okay.
The goal here is still to say some. I just understand what are we just studying the empirical risk at
local minima of yeah, I'm studying properties of the local minima of the empirical risk. Yeah.
So we're not claiming anything about the population.
No, I'm not claiming anything about the population. But the only reason I'm bringing up the population is to say that this, I mean, this is the, I guess, the more classical analysis of this kind of thing.
Want to do the population than we do here, but then at the proportional level, we cannot do this.
We cannot do this. Yeah.
Unless we see dimensions.
Okay. Okay, I guess this is just a setup so that now I can talk about the approach that we take. Okay, maybe I'll say approach we take. Okay, we do something similar in that we try to bound the probability that for x is theta in S complement such that this is true. But we try to do this via Markov's inequality. So we bound this by
Oh yeah, okay.
It's the same thing I've been talking about. So I'm going to bound this by following. So this probability is basically the probability that this random variable is bigger than or equal to 1. There's a theta in this set, then this size of the set is bigger than or equal to 1. So by Markov's, this is bounded by the expectation of this quantity. Right? And this, in turn, star bounded by the Kac-Rice theorem. Kac-Rice is the following statement. Given a process G from Rm to Rm, random process, and some regularity assumption. If I'm interested in the set Z of B, which is the set of T and B such that G of T equals 0, so the set of zeros of this process for T inside some set B, then this theorem tells me that I can compute the expected cardinality of this set as an integral over T and B of P of G of T, the density of G of T at 0 times the expectation, the absolute value of the determinant of the Jacobian of G of T conditional on G of T equals 0. Okay. Maybe I'll quickly just give intuition for those of you who haven't seen this. So here's a heuristic derivation of this. Suppose for simplicity, I'm going to take my G from R to R, one-dimensional process. I'm going to assume that G of T is equal to 0 only for finitely many T. And that G of T is continuously differentiable. And since this is a random process, I need to assume this on every sample path. So I'll assume this almost surely for any sample path. So I'm basically putting regularity conditions on my process so that it looks something like this. If I draw my process, it crosses 0 a few times in the interval A to B. And it's smooth enough. And so to compute the number of zeros of this thing, let's use the quantity I defined there. What I'm going to do is I'll look at an epsilon band of this guy. And I'll integrate from A to B the indicator that G of T is in minus epsilon plus epsilon. So I'm integrating the values of t that correspond to values of g within this band. Right now, I just get the length of this one plus the length of this one. I want 1 for each 0, so I'm going to scale this by the absolute value of g of t, by the slope at the point, and divide it by the width of this guy, t. And this becomes accurate as I take epsilon to 0. And I'm in the electrical engineering department at Stanford, so whenever I see something like this, I immediately write it as a delta function. Delta 0 g of t. Okay. So now I'm left with taking expectations of the left-hand side. I'm going to assume I have enough regularity to push my expectations into this integral. Okay, what is this expectation over? For a fixed t, this process is g and g prime are two random variables. They have some kind of joint distribution together. So I can always compute my thing as g prime of t conditional on g of t. And then I have my expectation over g of t outside. And I have my good old delta function. And this retrieves the form here. Conditional g of t equals 0. And when I integrate the delta function against the density of this guy, I get the density at 0. Okay. This is just the multivariate version of that, which is the one that we need. Okay. Anyone has questions, please ask now. Is this good? Can I erase it? Okay, so now I want to tell you about the results. But first, let me make the assumptions rigorous. Okay, the assumptions that I'm going to make are, first I'm going to assume my loss L and this labeling function psi, or generalized loss if you want, are regular. Okay, what this precisely means is, for instance, third order differentiable with Lipschitz derivatives. You can replace the Lipschitz derivative with something else, but let's say that's what it is for now. But in particular, for my first result, I'm not going to make any convexity assumptions. So I'm going to allow it to be non-convex for my first result. The second assumption is that xi are going to be isotropic Gaussian. Okay, you can ask me about the Gaussian assumption at the end if you want. And my wi are going to be IID sub-Gaussian. Third assumption is the regime that I talked about before, is that n over d converges to alpha, and alpha is in 1 to infinity. It's bigger than 1. And I'm going to assume that k, the number of indices, is order 1. This is the dimension of theta 0 and dimension of theta. And lastly, I'm going to put some kind of assumption on theta 0 on the limit of theta 0. Because once again, if I want to take things to the limit, I want to say something about the empirical distribution of these quantities. So I'm going to make the following assumption on theta 0. That the empirical distribution of theta 0 distribution of theta 0 converges in Wasserstein distance to some measure mu0, and this measure mu0 has a second moment that satisfies upper bounded by this and lower bounded by this in the PSD order. All this quantity R0, 0 throughout. So theta 0 is a D by K matrix. This is the empirical measure of the rows. So it's a distribution on RK. It has some kind of covariance, or uncentered covariance. And this covariance is well conditioned. Even if it's not random, yeah. So this doesn't require theta 0 to be random. It could be a deterministic sequence of theta 0s, but have some empirical distribution that's convergent. This is something like this. Okay. And I'll fix some notation now. I'll use X to be the matrix of features, Y to be the matrix of labels. Remember that my labels Y are in RQ, and then my theta is in D by K, so I'm going to denote its rows by theta 1 up to theta D. The same thing for theta 0. And like I mentioned, because I want all my results in terms of empirical measures, it'll be much nicer if I define what these things are, so I don't have to keep writing the subscripts. So the empirical distribution mu hat of theta, I'm gonna always denote it as the joint empirical distribution of theta, theta 0. Then I'll use mu hat of theta to be the empirical distribution of x theta and y. So this quantity in particular is in a set of distributions on k plus q, and this is in distributions on 2k. Okay. My first result is going to be a bound on the expected number of zeros. So first, I need to define for you what this expected number of zeros, what the set of zeros are that I can't quantify. So it's going to be the set of theta where the gradient is equal to 0. Just a stationarity condition. And I'm going to use A and B to localize my minimizers. So these are just some sets that are a subset of the set of distributions. And because I'm only interested in local minima, I'm going to put some kind of condition on the Hessian. Curvature condition that it's bigger than or equal to something. Ideally, I'd like to be bigger than or equal to 0, but because of regularity, I need this to not decay faster than e to the negative below n. And finally, I need some regularity condition on. I need to upper bound theta. See, guarantee that theta doesn't diverge, and there's one more regularity condition on this quantity that is bigger than. Okay. Okay, I'll say something about what this condition means. I'm going to write things a lot in terms of empirical distributions. So I'll say that first, when I say something like this, if you keep track of the notation, this just means that I'm writing I'm assuming that this is bigger than this guy. For instance, if you look at the case of k equals 1, what does this mean? This is saying that xi transpose theta squared is bigger than 0. At the minimizer, I'm going to have this quantity to be equal to 0. So saying that this is bigger than 0 or bigger than c, sorry, bigger than c. So it's saying that this quantity is not equal to 0 is saying that this is not 0 for a degenerate case. And the fact that it's a C and not just bigger than 0 is okay, proof difficulty. I think it's proof difficulty at least. Okay. But if you don't want to think about these assumptions, just think of this as the set of zeros that we can say something about. You have this empirical risk problem, and there might be a lot of great, critical points, but these are only critical points that we can capture with this theory. Things satisfying this.
This other mu hat, what'd you write mu hat sub?
Square root of d. So
Square root of d.
Yeah. Square root of d. This one.
Yeah, exactly.
So this is so I'm writing this matrix theta 0. This is a matrix in Rd by 2k.
This is just a concatenation.
Concatenation. Yeah. The norm of the columns of this matrix are order 1. So the elements are order 1 over root d. So I'm just multiplying root d so that the elements are order 1, so that this doesn't become something degenerate. Okay, I'll say maybe I won't be able to get through all of this, but I'll give the statement of the first theorem. The theorem is the bound on the expected number of zeros or critical points, or local minima, I guess, that satisfy this condition. And I don't bound it, I bound it on a high probability set. So omega is a high probability set. A and B satisfy some regularity conditions, some openness condition, and some topology. And now I'm going to give you a bound on this. This is, I'm working in dimension d, so generally this is an exponential quantity. So instead, I'll look at the log of this and divide by 1 over n. And the theorem states that this quantity is less than or equal to negative into mu, where mu are in some set B intersect A times B. These are the ABs that we started with, that we're going to use to localize our minima. Phi and nu are introduced by the theorem, so I need to tell you what they are. Phi is a function of measures, and it looks like so it's a function of mu and nu. There's an expectation over nu of this quantity, plus some other 9 terms that I'm not going to write down here, but they're in the paper. But I'll tell you what these, okay, it seems silly, but I'll tell you how this is useful. And then the set B, introduced by the theorem, specifies some constraint on the measures that you're optimizing over, and has, I don't know, maybe 7 terms that I'm also not going to write here, but they're given somewhat explicitly in the paper. Yeah, let me give our remark on that. So I'll give that as a remark. Here? This, yeah, this expectation is over. Well, so this grad L is really a function of Vy, and Vy are distributed according to nu. So I guess I'm throughout thinking of V as nu, the asymptotic distribution of nu hat, which is the empirical distribution of x theta y. And so I'm taking expectation of a quantity like this. I'm looking at the asymptotic version of the expectation of grad L. I erased here. Yeah. This thing?
The phi, I'm trying to understand the phi.
Yeah.
Large. To get the number of zeros small, we want phi to be large.
We want phi to look something like this.
Yes.
with a 0 only whenever you have a 0. Or if you have multiple zeros, you want it to be something like this. Okay. Okay, I'll say okay, maybe I'll skip one thing, but if I want non-vacuous bounds, so remember I wanted to use this as an upper bound in my Markov's inequality. So if I want non-vacuous bounds on the probability P, I would like, so if I do Markov, I get P is less than or equal to e to the minus n inf over phi mu nu, where I get whatever I have here. If I want this to be non-vacuous, I need to show that this quantity is bigger than or equal to 0 in the given setting that I have, right? You can try to do it on a case-by-case basis, but a harder thing to do is to do it uniformly. A harder thing would be, or like a nicer thing, but potentially harder would be to try to prove something like this. For some set S star, we have the following. Phi is bigger than or equal to 0 for all nu in the optimization set V, and phi is equal to 0 if and only if my measures mu and nu are in S star. This would help me localize my minima inside my set S star. Okay, today, I don't know how much of it I'm going to get through, but today I would do prove star if L is convex. And in preparation, I have a result for L non-convex. Again, I'll say that a bound like this was done in this paper by Antoine Millard and Benarus, and I think Biroli. And they derived something similar on the following loss, the following ERM problem. Simplified ERM problem. And they have some, they get something similar. They get also this bound in terms of some phi, but I'm not entirely sure whether this thing satisfies this property or not. This satisfying this property is just a function of tightness of this bound, right? If your bound is tight, then you'd expect it to satisfy this. And I don't know whether it satisfies this or not. Okay. If L is convex, I'm counting. Okay. There's one subtle thing here. So if L is strongly convex, I'm counting the unique minima, right? But now if L looks like this.
Yeah, but then there's infinity. Like if you have a convex function, I'm pretty sure you're always gonna have like infinity.
If you have a strictly convex function, if you have a strictly convex function, you're only going to have it diverge infinity, or it's going to have a unique minimizer, right? But you can have multiple minimizers if the landscape is flat. What do you mean?
Like, isn't that infinite minimizers?
Oh, infinite minimizers. Yeah, sorry, infinite minimizers. Yeah. And so, okay, the subtlety here is that the assumption I make here is on the risk. Right, and so I can take I can add a regularizer, perturb my loss with a regularizer to try to localize, minimizers of convex functions. But,
as long as you set lambda to be non-zero, it's already.
As long as you set lambda to be non-zero, it's strongly convex. But this holds for lambda equals 0 as well.
Yeah. So if it's strongly convex, then it has one unique minimum.
If it's strongly convex, it has one unique minimum. If the loss is strictly convex, but the problem is not strongly convex, then I have it's like logistic regression, right?
Okay, if lambda is positive, then do you have strict?
If lambda is positive, then it's strongly convex, and there's a unique minimizer.
Separable logistic regression.
That's strongly convex.
Strictly convex, but not strongly, and it has infinite. Right? That one's
Separable, yeah. Separable is
like
strictly convex. Exactly.
strictly convex, but has finite, but greater than one, but not infinity.
No, I don't think so. I would imagine not. I would imagine not. No.
Something very basic I'm missing here. So if lambda is positive, then
Yeah.
the Frobenius norm squared is just L2 norm of it, right? You do have
Strong convexity, yeah. Sure, yeah.
Yeah, then it's unique minimizer.
Unique minimizer. Yeah. If L is convex, yeah, we're done.
If L is
If
convex,
L is convex and this is bigger than 0, there's a unique minimizer.
then it's not interesting. Right? I mean, you're
So what's on it? Sorry.
the number of zeros
Will be 1. I think it's still interesting for the reason of results for multiple indices weren't available up to recently. Right? I think results for when the dimension, for instance, like the Gordon technology breaks when you have more than one index. It strictly doesn't work. There's a result, I think, in last year that came out for AMP that writes some set of complicated fixed point equations for the asymptotics of problems when k is bigger than 1.
number of
Not the number of points, the 1 point that you get from strong convexity. Yeah.
Yeah. So what are we estimating here? Because here in the theorem you estimate the number of zeros, the number of means, right?
This gives you the number of zeros, right? But the bound using Markov allows you to characterize. It allows you to localize. Okay, let me write it down because it's coming up next. Okay. So first, I'm going to write down this theorem abstractly, and I'm not going to write down what the set S star is, but let me say, if L is convex, once again, I don't need lambda to be bigger than 0. I can take lambda to be equal 0. If L is convex, then this property I holds for some set S star given by something that looks like f of mu nu is equal to
even if it is not strong.
even if it's not strongly convex. Yeah. Okay. So in this case, the statement would be something like this. So corollary of this is that if there exists a critical point theta hat and some constant C and C that are bigger than 0, such that theta hat is in the set and the regularity conditions that I had hold, then combining this with this theorem with the Markov bound that I did earlier would tell you that all epsilon bigger than 0, the probability that inf over measures mu star in the nice set S star, the Wasserstein-2 distance between the empirical measure of my theta hat and my mu star, mu hat, mu star. Probability that this is bigger than epsilon is less than or equal to e to the negative n c of epsilon for some c that's bigger than 0. So this gives you exponential exponential convergence in some sense of this thing to the set. Okay. Now, if this set, if S star is just, it determines mu star and nu star uniquely, then you have convergence in Wasserstein-2 distance. So I really intended to write down what these fixed point equations are to give you an idea what they are, because this sounds a little bit daunting, But when you write them down, it's not a fixed point equation, infinite dimensional parameters. It's order k squared parameters. And if you're familiar with like these techniques, these AMP techniques or Gordon techniques, the solution is always in terms of fixed point equations of some number of parameters. And these guys generalize those fixed point equations. And they're solvable. We solved them in our paper for logistic regression and used them to derive curves for the test error and the training error. Okay.
Will you have the constraint to have a finite one? Or how can you have like a constraint? Like for logistic regression, if you have a separable data.
If you have separable data, yeah. So this set of minimizers would be empty. This set would be empty. So the way we analyze it is we add lambda. We add a small perturbation lambda. Then it becomes strongly convex. Then you take the asymptotics and derive them, then take lambda to 0. And you can show that you can and show that you can do this in that order. And this tells you something about the lambda equals 0 case, even in the non-separable, even in the separable regime. So, I mean, in reality, we only added this lambda because it was nice for analysis. I think in general, I mean, I don't know why you would want to regularize this way, right? You probably don't want to regularize your matrix, but it helps with analysis. Okay. So I have 2 minutes. Can I write down maybe one more thing? Is that okay, or excuses that I started 3 minutes late? Okay. So I want to say that, like I said, these fixed point equations, this kind of solution, this kind of, fixed point equation, getting these solutions in terms of a fixed point equation isn't a new thing. And this was recently done for the case of k bigger than 1 using AMP. But one of the assumptions required to even derive the AMP results in that case was existence and uniqueness, or just existence of the solution of this fixed point equation. So generally, these are not a nice system of equations. You assume in advance that they exist, that the solution exists and sometimes unique, and then you show something about the limits of your problem to those solutions. Okay.
In this paper by Maillard et al., they were not. I mean, they were writing the equations, but they didn't know how to solve them. And in your case, you can.
Yeah. So they didn't know how to solve them, or they didn't know whether they had a solution. I'm asking.
No, I mean, I remember that they were writing this function phi, but they didn't know how to.
I see. Okay.
So I'm asking whether you know how to optimize it. Finally.
Oh, the function phi. You're talking about this function phi. I mean, we know how to do it in the convex case. I'm telling you that this is these are basically the first order optimality conditions for the function phi. Okay. I'm gonna say the following thing. So the measures mu solving the fixed point equation f of mu equals mu nu are in one correspondence to the following. Okay, maybe I won't write it down. To some convex problem. When the loss is convex, of course, that looks like this: G of Km. K is a matrix in R K by K, and M is a matrix. Yeah, okay, M is also in R K by K. This is some convex objective. The minimizers of this correspond in one have a one-to-one correspondence between solutions of this fixed point equation, and the correspondence is given by Okay, I'm not going to even be able to give it, but there's an explicit correspondence between the solutions of this guy and that guy. And some properties of this function is that in the case when the loss L is strictly convex, this problem is strictly convex. In the case when it's strongly convex, this problem is strongly convex, and so on. So this explicitly tells you when you can solve this system and when you can't. Okay, unfortunately, not much.
The correspondence is to the minimizers of this condition.
Yeah. The minimum of these guys correspond in some way to measures. That's that guy. Yeah. So minimizers. Sorry, the minimizers.
All right, let's thank Basil. Are there any questions? If there are no other questions, let's just thank Basil another time. Let's